Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
We'll be looking at virtual work. For this particular problem, we want to determine the angle theta required for equilibrium as well as the value of W when theta required for neutral equilibrium when theta is zero. Okay, to solve this problem, we will determine the potential energy function, okay, and differentiate it with respect to theta, setting it to zero and solving the resulting equation to determine equilibrium position. While for the uh, neutral for W, we'll take a second derivative of the potential function with respect to theta and set it to zero and solve, imputing theta to be equal to zero and solve to get W. Okay, all right. So this is theta. This is theta here. All right, we have this. Okay. All right, so we have that, and this is L. This length is L. All the members, they are L L. Okay, these ones are L L length that I've already signified. Now for the spring, we have the force coming like this, and like this, the spring force here coming in that direction. Let's call it F source with S, and this F source with S. And for the displacement, for the spring for this one, let's call it S. And for this, let's call it S. All right. So the spring has a constant K. All right. So if we consider the weight there W, we can find the height to be Y to be equal to two L cos theta. Because this is from here we get L cos theta. Then the other length L cos theta. So it's going to give us two L cos theta. Okay. Then considering this center of gravity where this weight is acting through, so we call it let's call it from here to here ish. Okay, this height ish. So we're going to add h to here. All right. So we have that so that the potential gravitational potential energy is going to give us this W times Y. All right. Of course, we are taking our datum from the bottom here. That is, let's call this line, okay, is AB. All right. All right. You can see that we are going to have a positive gravitational potential energy since the center of gravity there is above the datum there. All right. For the spring, we are going to have V. Let's call it V source with ED, elastic potential energy. We are going to have this for one of the springs. So we are talking about two forces. You can see this force coming and this force coming there. So half K is going to give us half K S square plus half K, where K is the spring stiffness square. You can just get our S direct to know what S is. It's going to give us from here, it's going to give us L sine theta for one. So for the two, is going to give us 2L sine theta, sine theta. So we have that. All right. Then if we want to get S squared, if we square this, considering that the relation S is squared there, we're going to give us 2L sine theta. Okay. So we can now square it. So we have this. All right. Have that. All right. So we can just plug in this into the potential energy function. So call it V. So sorry, the potential function will give us that. We have these, okay, V sub with G plus V sub with E, gravitational potential energy and the elastic potential energy, so that if we plug in all our values in there, we are going to have V to be equal to um, to just plug in all the values we've gotten so far for V sub with G and V sub with E. We'll have this cos theta plus H. Okay, so plus H. Okay, so remember that our Y we are just multiplying by W there. Okay, that's why we have uh, this. Okay, to get multiply our Y by W. Okay, because this is the same thing. This is the same thing as W times Y. Okay, all right. So for here for the spring, we are going to have this to be 2K, 2K spring constant L squared sine squared there, square theta. So that's what we are going to have. Now, if we for equilibrium position, we can just for our equilibrium position, we have this. So if we take the derivative with respect to this, we are going to have with respect to theta. So if we do that, we are going to have it to be 2 pi minus 2 W L sine theta. Okay, sine theta. All right, plus sine theta. Sine theta plus 2k 2k L square sine 2 theta sine 2 theta. Now remember we put it to 0 for the equilibrium position. We put the derivative to 0. So if we remember that sine 2 theta is same thing as 2 sine theta cos theta, so that if we plug in everything there and bring W sine theta to the other side, we are going to arrive at W sine theta, okay, to be equal to K L times 2 KL times 2 sine theta, okay, cos theta. All right, so we have that. Then we can just go ahead and just find cos theta from here. Of course, we know that sine, we cancel sine from this, we go, okay. So we can have our W. We can just make find our theta from there. So theta is going to give us the arc cos of W over 2 LKL. So this is the equilibrium position. Okay. Now we can now talk about the stability. Okay. And remember, we are looking at neutral position. We are looking at neutral stability. Okay. So if we do that, we take the second derivative. Okay. Take the second derivative. We will have this to be equal to, of course, this we also set it to 0. That is the condition for that. All right, so that if we do that, we are going to arrive at -2. Take the second derivative, minus 2W L cos theta, that's what it's going to give us, plus 4KL plus 4K, okay, L square cos 2 theta, L square cos 2 theta, which is equal to 0, as I said. That's the condition, you set it to 0. Okay, set it to 0. Then haven't done that, so to see the 0 here, Okay, that's because of the space. Put it there, set to 0. So if you plug in 0 as theta as 0 from the question, we are going to arrive at W to be equal to 2. W will be 2 K L. So that's what we are going to have as. This is W when theta is the value of W when theta is at 0. Okay, for neutral stability or neutral equilibrium. Okay.